Hi folks, today we want to revisit double displacement reactions with the objective of learning how to accurately predict if such types of reactions will happen when two aqueous solutions of different ionic compounds are mixed together. Recall that one of the ways of identifying a double displacement reaction is when a precipitate is formed. However, there are other types of double displacement reactions that happen that do not involve precipitate formation. These are reactions between aqueous solutions of acids and aqueous solutions of carbonates. These are identified by effervescence with the evolution of colorless carbon dioxide gas that turns lime water milky. The reaction between solutions of strong bases and solutions of ammonium salts. These reactions are identified by the evolution of a colorless, pungent-smelling ammonia gas that turns damp pink litmus paper blue. And finally, the reaction between solutions of acids and solutions of bases. And these are identified by a change in pH of the mixture and the evolution of heat. However, today we want to focus more on those double displacement reactions that produce precipitates. Written on the board are the chemical equations for the mixing of two different sets of ionic compounds. The first one involves the mixing of sodium chloride solution with potassium carbonate solution. Notice how we have formed the products there, but we did not insert any subscript there. Normally, we put in liquid, aqueous, solids, gas, and stuff like that. We did not insert any of that. Reason being that we do not know if either of these is a precipitate. We know that a precipitate is formed because that product is insoluble in water. And to know whether or not a reaction will happen, we need to determine the solubilities of the products there that we've written. This is provided by a solubility chart. And we can look at a solubility chart in this book here that I've written. It's called Chemistry 11 in Focus. Okay? And we'll now look at the solubility chart inside here. And we'll try to determine the solubilities of the products in both of these reactions here. This one here is for the mixing of potassium bromide solution with silver nitrate solution. I get potassium nitrate and silver bromide here. According to the solubility chart, both sodium carbonate and potassium chloride are soluble in water. As such, we'll now put in the aqueous subscript there. Aqueous means that both of these are soluble in water. However, the solubility chart indicates that potassium nitrate is soluble, but this guy here is sparingly soluble. So I put in aqueous here, and I put a solid here. So in that case, because this silver bromide here is sparingly soluble, we will expect a precipitate to be formed. So what we'll do now, we'll test our predictions, okay? We'll test our predictions by mixing these solutions together. This one here is the mixing of sodium chloride solution with potassium carbonate solution. Okay. We expect nothing to happen. Bravo, same thing, nothing happened. Now we'll react or we'll mix potassium bromide solution with silver nitrate. We expect a precipitate to be formed now. See? Yes. See? So our predictions were right. That's a precipitate of silver bromide there. Okay? The whole thing is looking cream. If you leave this for a few hours, the silver bromide solids will precipitate under the influence of gravity. So you see two phases there, okay? So quickly, just want to talk a little bit more about these two reactions here. Of course, now that a reaction has taken place there, we can write the ionic equation for that reaction there. I knew what it was, that's why I finished it before, because I didn't want to waste time. So if you remove the spectator ions now, what you will left with is a net ionic equation here. Silver ions reacting bromide ions to give you solid silver bromide. This test tube will look This one here will appear like this sooner or later. We're going to see this solid, and we have clear solution of potassium nitrate. All you'll find inside there are potassium ions and nitrate ions. This one here, nothing will happen because these will be floating freely inside there. Okay? In the following activity, we will mix in 5 different sets of solutions, of course, with different compounds dissolved inside. The first thing we will do is write in the equation for the reaction. Secondly, we will use the solubility chart to find the solubilities of these. If both of them are soluble in water, we then write in the subscript here, AQ, to show, and therefore no reaction will take place. If it is found that one of them is sparingly soluble, as in this case, put in S, okay? And then the other one, of course, has to be AQ. Both of them will not be solids. Anytime you have a double displacement happening when you have a precipitate being formed, only one of the products is a solid, the other one is soluble in water. And finally, you'll test your predictions as I have done there just now with these 2 solutions here. Well, we'll now go on to teaching you how to use the solubility chart. You see the solubility chart does not have all the compounds there, which are soluble and which are insoluble. These are hundreds and hundreds of compounds. But there are some guides there that will allow you to know which compounds are soluble from which are sparingly soluble in the solubility chart. This is one of the most challenging things to do, is to learn how to read the solubility chart to ascertain the solubilities of compounds. So we now move on to doing our activity. Our first reaction will be that between aqueous sodium carbonate and aqueous zinc chloride. So now we will try to predict whether either of these is a solid or both of them are aqueous. So what we do here, we do your double displacement. See, I did not put aqueous or solid in either of them, right? So then next, what did I do? I broke these up into their respective cation and the anion. So what we'll do now is we'll use a solubility chart to see the solubilities of these ones here. This here is a solubility chart. Listen attentively. These are the anions that cations react with. See, the first column gives you all the anions. This second column here and this third one relate to the various cations. Now, the cations in the second column here, if they react with the anions on the left side, they will form salt that is sparingly soluble. Okay, for example, if I have lead here, lead can react with all of these here, bromine, bromide, chloride, and iodide ions to form precipitate. Now, in the same row here, these cations here, you don't see any cation, which means all the cations except these. So if you look at the periodic table, lots of metals are there. It will be too tedious to write in all those cations here. So we identify these here as being the cations, which if they react with these on the left-hand side, they'll form precipitates. All other cations will not form precipitates with these ions. So same thing for these. Look at this one. Look. You want to know the solubilities of hydroxide, right? Only these few ones there, along with hydrogen, should put in hydrogen there too, will form hydroxides that are soluble. Okay, all the rest will form insoluble hydroxide, but their space is too deficient there to insert all of those other ones. So we'll go, if you want to know if something is soluble or not, check the ones that are given. If it is found here, it means it's soluble. If it is not found here, it means it belongs to this column here, which indicates insoluble compounds. Okay, this is what we'll do now. We'll check for the solubility of sodium chloride. Okay, so we'll look at where chloride is, and then we'll check to see where is the position of sodium. So look, Chloride is in this column and this row here. Now we want to see if sodium is here. Sodium is not amongst these, it must be here. So sodium chloride is soluble in water. So I'll now go and put aqueous there, okay? So we know that is a solution. Now we'll check for zinc carbonate, okay? So go where carbonate is. Carbonate is down here. They've given you a few of them that are soluble. Check to see whether or not zinc is amongst these. Zinc is absent from there. So it means that zinc must be inside here, the ones that are insoluble. So we now say that zinc carbonate is insoluble. So now you're going to put S here. Okay, now you can formulate your net ionic equation. Sodium ions, common ion there, okay? What else is common? Chloride ions here. So your net ionic equation will be zinc ions reacting with carbonate ions to form a precipitate of zinc carbonate. Now you'll do the reaction. Okay, so you can see a little bit of white precipitate is formed there as a precipitate of zinc carbonate. Now the second reaction that we're doing has to do with the reaction between iron 3 chloride and sodium hydroxide. Like we did before, we'll do a double displacement. Now we have OH and iron, and we have sodium and chloride. Now, let's check the solubilities of sodium chloride. So we're looking at this anion here, that cation. So we put our solubility chart here now, and then we try to see where chloride is. See, chloride is here. Look to see if sodium is amongst these insoluble ones that are given. It's not here, therefore sodium belongs to this column here, and therefore sodium chloride is soluble in water. So we'll now go and put aqueous here. We put an aqueous sign here, AQ, okay? Oh, we knew that from before, the other one too. Now we want to see whether iron 3 hydroxide is soluble or not. We'll go where OH is on the anion side, so OH is here. Now, we're given that all of these guys here are soluble, okay? We want to see whether or not iron 3 is amongst these. Can we see that? Iron is absent from there. Fe3 must be in this one here. Therefore, we expect iron 3 hydroxide to be insoluble. So we now come and put S and S here. So we expect a precipitate. Why don't we check that out? So now, react that here. We have iron and OH. You can see right away now you get a reddish brown precipitate. So we are correct in our predictions. Okay, let's see what is the other reaction now. Okay, third reaction is between. Oh, you can go ahead and do your net ionic equation. You break all of that into the ions, remove the spectator ions there, sodium is spectator ions here, and what is left really is this one here, the iron 3 reacting with the OH here to give you your precipitate of iron 3 hydroxide. Now we look at another reaction, the one between potassium nitrate and magnesium chloride. Again, do your double shift, you get these compounds being formed here, split them up into their respective cations and anions, and then check out the solubilities of each compound. So we have potassium versus bromine. So now let's see the solubility of that. Potassium versus bromine. So bromide ion is here, okay? And now we check to see if potassium is present here. Potassium is absent from there. It means that potassium must be in here, and therefore that compound will be soluble, okay? So we say that this guy is aqueous. Now we check the solubilities of nitrate, magnesium nitrate. Go to see where nitrate is. Nitrate is down here. Nitrate is right at the bottom. And you don't have any cation that forms a compound with nitrate. They're all soluble. So what we say now is that this is also be aqueous. So when you mix those two, you expect not to have any precipitate. Let's try that out there and see what happens. Here, expect no precipitate to be formed. Nothing at all. You see that? Okay, so predictions are going nice. What do we have? We have a reaction between now sodium carbonate and hydrochloric acid. So we do a double shift. Now we check in the solubilities of sodium chloride. We did that before. We did this one before. We know it's aqueous. Okay. Now we go to carbonate and hydrogen. Okay. So carbonate is here and hydrogen is here. Okay. So it means it's soluble. So you're going to see hydrogen carbonate solution is soluble, but you need to know something else. When the acid reacts with carbonate, it forms carbonic acid, right? But because this carbonic acid is unstable, what it does, it breaks up into carbon dioxide and water. So whenever an acid reacts with a carbonate, you will see effervescence, and that indicates the liberation of carbon dioxide, and a reaction does take place, even though this guy here is aqueous too. Let's do that reaction, see what happens. We're expecting some effervescence to take place. We see some bubbling taking place. See that? So you did see effervescence happening. The gas that comes on there is carbon dioxide. The other reaction that we have here is a similar reaction to this one, but it involves the reaction between potassium hydroxide and ammonium chloride. Again, we do our double shift. Potassium takes the place of ammonium ions. Ammonium ions take the place of potassium ions, and that's how we head. Break these into the cations here. So we now check the solubility of chloride ions with potassium there. Okay? So go where chloride ion is located. Chloride ion is here. Is potassium amongst these? No, it must be in this column made as soluble. So we can now see that it's a soluble compound here, aqueous. Now we check the solubility of OH and ammonium ions. Okay? So OH is here. Ammonium is amongst these ones that are soluble. Okay? So we say that ammonium hydroxide is soluble. Okay? But just like we talk about carbonic acid, in this form, it is somewhat unstable, so it breaks up to give you ammonia gas and water. So both of these are aqueous, but a reaction does take place because when ammonia is formed, it breaks up into ammonia and water. We expect a colorless solution to be formed, but only in this case, ammonia gas will be liberated, and we can check for that. We can check for the liberation of ammonia gas by inserting indicator paper there. Ammonia is a pungent smelling gas that turns pink litmus paper blue, or it changes the color of pH paper. So we check both of them out and see what will happen, okay? We'll damp these. These are the colors of the papers before. So what we'll do now, we'll insert one of them there. And then now we pour in the other solution there and see if you see any change in the color of these. See that? You can see the pink litmus paper went blue, and you can see the color of the pH paper change. So that indicates the presence of ammonia gas. There's a third type of double displacement reaction that happens in which you do not see a precipitate, and that is between acids and bases. It's saying that the reaction between an acid and a base does not produce a precipitate, so you won't be able to say whether or not a reaction is taking place. But you can see that by using indicator paper. So here's a base here. It changed pink litmus paper to blue, and that's the color on pH paper, right? Okay. Now what we can do here also is doing this. We can maybe put in a drop or so of phenolphthalein inside. Okay. So that's phenolphthalein indicator. So what we'll do now, drop by drop, we'll pour some hydrochloric acid into that and see what happens. This part is very strong. Can you see that now? The phenolphthalein has changed color to colorless. That means we have now an excess of the acid there. Okay, neutralization has happened. Again, we'll check that with pH paper and litmus paper. So in the first case, the base was able to change pink litmus paper to blue. Let's see where or not there's a change now. Right, see? Now the solution is acidic. So whenever you have an acid and a base, a reaction will happen. So there are three ways by which a double displacement reaction can be known. One, a precipitate formation. Number two, liberation of a gas reaction between carbonates and acid. Liberation of ammonia between ammonium salts and strong bases. And in this case, between an acid and a base.